Older language models like RNNs read text the way we do, one word at a time, from left to right. Transformers take an entirely different approach. They read the entire sentence all at once. Because computers can't process letters or words, the system first maps every word to a continuous numerical vector of a fixed dimension, often 512 numbers long. We call this a token embedding. This animated diagram shows how we solve the model's lack of word order. Because everything is processed in parallel, we use this formula. X equals the embedding plus a positional encoding. The word code becomes a vector array like 2.0, 3.0. We then add a specific array generated from sine and cosine waves, here 0.5 minus 0.5, giving us a final input array of 2.5, 2.5. By adding these two arrays together, the model receives a single vector that contains both the definition of the word and its exact mathematical location in the sequence. Fusing these two elements together is what makes simultaneous processing possible. This brings us to the attention engine. We multiply the input by 3 learned weight matrices to create queries, keys, and values. This formula right here shows how they interact. We first multiply the queries by the transposed keys. This step generates a raw mathematical similarity score between every single word and every other word in the sequence. Notice the denominator and the softmax function directly beneath it. Here we hit a mechanical friction point. With large embedding dimensions, our raw dot products grow excessively large, producing scores of 100 or more. If we feed a raw 100 into the softmax function, it outputs hard ones and zeros. Gradients vanish and the model stops learning. By dividing that 100 by the square root of the key dimension, say the square root of 64, which is 8, we scale the score down to a manageable 12.5. That scaled down number allows the softmax function to output smooth, usable probabilities. We then multiply these weights by our value matrix, dictating exactly how much focus the target word should pull from its neighbors. The scaling factor is not a random, arbitrary division. It is the exact mathematical safeguard preventing the network's learning gradients from dying out as the dimensions scale up. Rather than running this attention process once, the model splits the calculation into several smaller parallel chunks known as heads. This allows one head to track grammar, while another simultaneously tracks character actions, before concatenating everything back into a single vector. After attention, we hit a residual connection. The original input vector is added straight back into the attention output, creating an uninterrupted highway for gradients to flow backward during training. Then we apply layer normalization. This formula handles the normalization step for an input array of 2, 4. First, we calculate the mean. The average of 2 and 4 gives us a mean of 3. Next is the variance. We take the average of the squared differences from that mean, which gives us 1. By subtracting the mean and dividing by the square root of the variance, our original array of 2, 4 normalizes perfectly into -1, 1. These two mechanisms work in tandem. The residual connections secure the learning pathway across deep layers, while the layer normalization mathematically forces the changing data into a perfectly balanced distribution around 0. The stabilized data then passes into a position-wise feed-forward network. A linear transformation uses a weight matrix to project the data into a much higher dimensional space. Take a look at this FFN formula highlighting the ReLU activation function and the input vector of -3 and 5 below it. Pause for a second and try to calculate the exact output of that vector when it passes through the ReLU function, which outputs the maximum of either 0 or the input number z. The correct array is 0 and 5. The ReLU function simply replaces any negative number with a 0 before a second weight matrix projects the data back down to its original dimension. Applying this nonlinear mathematical filter isolates the most important features in the data. After that, it passes through one final round of residual connections and layer normalization. This animation shows our final output vector passing through a linear layer. It expands the vector out into a massive bar chart of unnormalized raw scores, called logits, representing every single possible word in a 50,000-word vocabulary. We apply the softmax function one last time. It normalizes these thousands of raw scores into strict probability percentages. Notice how one bar clearly peaks above the rest at 85% for the word Python. The system simply selects the index with the absolute highest percentage. That specific word becomes the model's official prediction for the next step in the sequence. Looking at this complete pipeline cheat sheet, we can trace the exact mathematical path. We start with the input plus positional encoding, move through the scaled multi-head attention, apply the add-in norm, run it through the feed-forward network, hit add-in norm again, and finish with the linear and softmax layers. By carefully orchestrating these scaling factors, residual highways, and normalizations, we mathematically guarantee a system capable of processing entire sequences of language simultaneously without collapsing during training.